Hello everyone. Today we are starting chapter 9, the behavior of fluids. So let me ask you a quick question to think about. Why do you think a heavy steel boat can float, but if you drop a small piece of metal into water, it sinks right away? Or here's another one. Why do some objects float while others sink? Is it just about how heavy they are, or could the shape and the forces in the fluid play a role? So in this chapter, we will explore ideas like buoyancy, density, and pressure in fluids to answer these everyday puzzles. So by the end, you will have a clearer understanding of why objects behave so differently in water and other fluids. So as you go through the lecture, keep asking yourself, what makes this object sink or float? And how does pressure in a fluid affect the world around us? So let's dive in. Now these are the learning objectives for this chapter. So by the end, you will be able to first understand pressure and atmospheric pressure. So think about this. Why do your ears pop when you fly? Or why does soda fizz when you open it? That's pressure in action. Next, you will see how pressure changes with depth. So imagine diving into a pool. Why does it feel harder the deeper you go? So keep that question in mind as we explore. Finally, study floating objects and fluids in motion. So why do ships float? And why do rivers flow faster in narrow sections? We will find out together. So as you watch, try to think of examples from your own life. Maybe even pause the video and jot one down. Now let's take a look at the chapter outline. We will start with pressure and Pascal's principle, where you will see how force is transmitted through fluids. Next, we will explore atmospheric pressure and the behavior of gases. Air around us plays a bigger role than you might think. Then we will dive into Archimedes' principle to understand why objects float or sink. So before I explain, take a moment to guess whether a few objects near you would float or sink. You might be surprised by some of the answers. Finally, we will study fluids in motion. So how do fluids and gases flow? And why does water speed up in narrow pipe? Think of rivers, hoses, or even water swirling down a drain. You will start to see the patterns in action. So as we go through each section, try to connect what you are learning to real life examples. Observing these principles in your daily life makes the concepts easier to understand and more fun. Now let's start by understanding pressure. So we define the pressure as the ratio of the force to the area over which it is applied. Symbolically, it's written as P equals F divided by A. And the units of pressure is Newton per meter square because force is in Newton and area is in meter square. Right? That's the standard unit. Now there's also another special name for this unit. We call it Pascal. So 1 Pascal is equal to 1 newtons per meter square. But what does this mean in real life? Let's think about an example. So why does a small woman wearing high heel shoes sink into soft ground more than a large man wearing a big shoes? So take a moment to think. Can you explain this using what we just learned about pressure? So here's the idea. When you walk, almost all of your weight is supported by your heel at some moments. And as you move forward, the weight shifts from heel to toe. You can even try a few steps and feel it yourself. Now a woman's high heel shoe has a very small heel area, maybe just 1 or 2 square centimeters. So how do you find pressure? Pressure is force over area, right? So when her weight is divided by the tiny area is small, so it produces a larger pressure on the ground. So how about the man? So his shoe has a much larger area. Area is larger, right? Maybe 100 centimeters square for a size of 13 shoe. So even if he weighs 2 or 3 times more than the woman, his pressure on the ground is actually smaller because the force is spread over a large area. Area is large, therefore pressure is smaller. So the woman's small heel creates a high pressure which sinks more into the ground, while the man's larger shoe spreads his weight, creating a smaller pressure and a smaller indentation. So try to look around and find other examples where the same weight on different areas produces different pressures. Maybe a nail, a snowshoe, or even a sled on snow. So how does pressure play a role there? Now that we have talked about pressure, let's move on to our next topic, Pascal's principle. So what happens when we apply pressure to a fluid? Take a look at this figure. We have a piston pressing down on a cylinder filled with water. So what do you think happens when I push the piston down? So when we push the piston down, the piston applies a force on the fluid and the fluid gets squeezed just like a compressed spring pushes back. So just like a compressed spring pushes back, the compressed fluid pushes outward on the walls, on the bottom, or even back up on the piston. So this shows us something important. The fluid doesn't just push in one direction. It pushes uniformly in all directions when compressed. So that means any increase in pressure in a fluid is transmitted equally throughout the fluid. And this is the essence of Pascal's principle, discovered by the French scientist Blaise Pascal. So in simple terms, Pascal's principle says any change in the pressure of an enclosed fluid at rest is transmitted uniformly to every part of the fluid. And this principle is powerful. It's the basis of hydraulic systems. You see them in hydraulic jack lifting a car or in the brakes of your car. Now let's see how a hydraulic jack works. Have you ever seen one in action? Hydraulic systems are used to lift heavy objects by applying a surprisingly small force. So hydraulic systems are a perfect example of Pascal's principle. So look at this figure. We apply a force to a piston with small area, which produces a large increase in pressure in the fluid. So why does this happen? Because the area is small, the same force creates a higher pressure. And this pressure is transmitted through the fluid to the large piston on the other side, according to Pascal's principle, right? The pressure applies uniformly throughout the fluid. And here's the key point. Pressure is force per unit area. So the force on the larger piston is calculated by F equals PA, right? Here force is, if you isolate force in this equation, you get F equals PA, pressure times area. Now the second piston has a much larger area. Area is larger. A2 is larger than A1. So the same pressure produces a much larger force. Why? Because area is larger. We have the same pressure but area is larger. So that's why a hydraulic jack can lift a car even when you push with a smaller force on the smaller piston. So think about it. Next time you see a hydraulic lift at a mechanic shop, you will know the physics behind it. So we will go through a numerical example next to make the concept even more clearer. So let's work through an example to see Pascal's principle in action. Suppose we apply a force of 10 Newton to a circular piston in a hydraulic jack, and the area of this piston is 2 centimeters square. And the output piston has a much larger area of 100 centimeters square. 100 centimeters square. Now pause the video and try to calculate the pressure in the fluid before we continue. So you should get the answer as D 50 kilopascal. So let's solve it. Now we have been given the force applied at the smaller piston, which is F1 equals to 10 Newton and its area 2 centimeters square. So we need to convert the area to square meters. So we have to divide it by 100 times 100, right? 100 times 100. This is centimeter square. Therefore we get 0.0002 meter square. So what is the pressure then? Pressure is defined as force divided by area. So for piston 1, we have force 1 divided by area 1, right? So force 1 is 10 Newton and area is 0.002 meter square. Therefore we get 50,000 newtons per meter square, right? So what is newtons per meter square? It is Pascal. And this is 50,000. So therefore we can write it as 50 times 10 to the power 3 Pascal, or 10 to the power 3 means kilo, right? Remember? So this is 50 kilopascal. That is the pressure in the liquid. Now according to Pascal's principle, this pressure is uniformly distributed throughout this liquid, right? So this same 50 kilopascal acts on the larger output pistons as well. Now let's see what happens on the larger piston. So we already calculated the pressure in the fluid is 50 kilopascal. And according to Pascal's principle, this pressure is uniformly distributed and acts on the larger piston, as I said in the last slide. Therefore, pressure on the larger piston is again 50 kilopascal, which is 50,000 newtons per meter square. And now we know the area, which is 100 centimeters square, and again you have to convert it into meter square by dividing 100 times 100, because this is centimeter square, and we know that 100 centimeter is 1 meter, right? Now we can find the force on the output piston using the equation F equals P times A, because we know that pressure is force over area. Therefore force is pressure times area, and we know the pressure, which is 50,000 Newton per meter square, times area is 0.1 meter square. So here meter square will cancel out. You will get the answer in Newton. The unit of force is Newton, right? So you will get it is 500 Newton. So the answer is B. Now see how a small input force of 10 Newton on the smaller piston can create a much larger force of 500 Newton on the larger piston. So that's the power of Pascal's principle in hydraulic systems. So take a moment to pause and think. This is exactly why hydraulic jacks can lift cars so easily with a small push on the smaller piston. Now let's pause and reflect. So this wraps up the first section of the chapter on pressure and Pascal's principle. Think back to what we have covered. Pressure is the ratio of the force to the area over which it is applied, F over A. So can you think of other examples from daily life where a small area creates a larger pressure? So pause and think of one example. Next, we learn about Pascal's principle, which tells us that changes in pressure are transmitted uniformly through a fluid, and the pressure pushes outward in all directions. So can you visualize this happening in a hydraulic system, or even when you squeeze a water-filled bottle? And finally, we saw how these ideas explain in hydraulic jacks and other systems. So think about the last time you saw a car being lifted with a jack. Now you know why a small push can lift something so heavy. So take a moment to pause the video and try to name at least one real life situation for each of these points before we move on. So connecting these concepts to everyday life will make them easier to remember. Now let's move on to atmospheric pressure. So we live on Earth, right? And the Earth is surrounded by a huge layer of air. You can think of it like we are at the bottom of sea of air. And this air has weight. And the pressure exerted by all the air above us is called atmospheric pressure. So here's a fun fact. Air is a fluid just like water, and it has weight. That means all the molecules of air above you are pushing down, even though you don't feel it directly. And at sea level, the atmospheric pressure is about 100 kilopascal, which is also called 1 atmosphere or 1 atm. But here's something to think about. The air is thinner at higher altitudes. That means as you go up a mountain or fly in an airplane, there's less air above you and the atmospheric pressure decreases. So now we know that the pressure we experience is due to the weight of the air above us. So why don't we feel squashed by it? Pause and think about this for a moment. Answer is that our bodies have internal pressure. So air permeates our lungs and the other parts of our body so that the pressure inside us balances the pressure outside. That's why we don't feel crushed by the atmosphere. Now here's another interactive thought. Imagine climbing a very tall mountain. And as you go higher, there's less air above us, right? So what effects do you think this could have on your body? Breathing becomes harder because there is less oxygen and lower pressure. So in summary, atmospheric pressure decreases with altitude because there's less air above you. So you can even test this idea by noticing how your ears pop in an airplane as you change altitude. So take a moment again to pause and picture it. Stack all the air above you like layers. So at sea level there are many layers and on a mountain there are fewer. That's why pressure changes with height. Now that we are talking about air, do you know the difference between gases and liquids? So the main difference comes from how their atoms or molecules are arranged or packed. So take a look at this figure. In a gas, the molecules are separated by large distances compared to their size. So they have lots of empty space between them. But in contrast, in a liquid, the molecules are closely packed, almost like a solid. That's why liquids cannot be easily squeezed. So here's something interesting. Gases behave a lot like springs. They can be compressed into a much smaller volume if you apply pressure. And they can expand if the pressure is reduced. Remember how we talked about air being thin at higher altitudes? So that's because the number of molecules per volume is lower. At higher altitudes, the pressure is low, so the gas expands, making the air less dense. Now this brings us to an important point. The density of a column of air decreases as altitude increases. So here density is defined as mass divided by volume, and it tells us how packed the molecules are. Now can you think of any examples where you have seen a gas expand or compress, like in a balloon or an aerosol can? So pause the video and try to come up with one example before moving on. So this slide helps us understand the behavior of gases and why air pressure and density change with altitude. Now let's talk about how the pressure of a gas affects its volume. So a scientist named Robert Boyle studied this relationship through careful experiments. So he discovered something important. The volume of a gas is inversely proportional to its pressure. So in other words, Boyle's law tells us that P times V is constant, where P is the pressure and V is the volume of the gas. So what this means practically is, if the pressure increases, then the volume decreases, so that the product P times V stays the same. And if the pressure decreases, then the volume expands. So in this equation, P1, V1 are the initial pressure and volume of a gas, and P2, V2 are the pressure and volume after a change. Because pressure times V is a constant and this is a constant. So this formula is very useful for solving real life problems, like calculating the behavior of gases in syringes, balloons, or even in scuba tanks. So remember, P1 V1 equals P2 V2 is just another way to express Boyle's law, linking pressure and volume in a simple, predictable way. Alright, let's look at a practical example of Boyle's law in action. Imagine we have a cylinder with a movable piston, and inside there's a fixed amount of gas. Initially, the gas has a pressure of 1 atmospheric pressure. So P1 is 1 atm, which is about 101 kilopascals, right? And a volume of 0.3 cubic meters. V1 is 0.3 cubic meters. Now what happens if we increase the pressure to 3 atmospheres while keeping the temperature constant? So now new pressure is 3 atmospheric pressure. Pressure increases. Now we are asked to find the volume V2. So before I solve it, pause and take a moment to try it on your own using Boyle's law. P1 V1 equals P2 V2. So if you solve it correctly, you should get the answer A 0.1 meter cube. Now we have two conditions. Initially, P1 equals 1 atm and V1 equals 0.3 cubic meter, and finally after increasing the pressure, we have P2 equals 3 atm and we want to find the new volume. Alright, let's solve it together. So here we are applying the Boyle's law, which is P1 V1 equals to P2 V2. Now what is P1? It is 1 atmospheric pressure, 1 atm, V1 is 0.3 cubic meter, and new pressure P2 is 3 atm, and we are asked to find V2. So what is V2? V2 is 1 atm times 0.3 cubic meter divided by 3 atm. So the answer is 0.1 meter cube. So that means when the pressure triples, the volume shrinks to a third. So can you explain why this makes sense intuitively? It's because we know PV is a constant, right? So increase in pressure squeezes the gas into a smaller space. That's why when we triples the pressure, the volume shrinks to a third. Now let's see another real life example of Boyle's law. So this time with scuba diving. So imagine a scuba diver releases a bubble of air at a depth of 40 meters, which is roughly the maximum depth for an experienced diver. Now at this depth, pressure is about 4.9 atmospheric pressure. 4.9 atmosphere. So the bubble has a volume of 2.5 cubic centimeter. So volume 1 is 2.5 cubic centimeters. Now the question is, what will the volume of the bubble be when it reaches the surface? So we are asked to find the new volume. So what is the pressure on the surface? It's only 1 atmospheric pressure, right? Now pause for a moment and try calculating it yourself using Boyle's law. P1V1 equals P2V2. So let's solve it together. We know the initial condition of the bubble when he released it, P1 and V1. And at the surface, the pressure is just the atmospheric pressure, which is 180 m. So now we can find V2 using the equation P1V1 equals to P2V2. Now what is P1? It is 4.980 m. V1 is 2.5 cubic centimeters and P2 is 180 m, and we asked to find V2. So what is V2? V2 is 4.980 m times 2.5 cubic centimeter divided by 180 m. Therefore, the answer is 12.25 centimeter cubes. So here I didn't convert centimeter cube to meter cube. Therefore, I am getting the answer in centimeter cubes. So here the bubble expands nearly 5 times as it rises to the surface because the pressure drops. And with that, we have reached the end of section 2 on Boyle's law. Alright, let's quickly review what we have learned in section 2 about atmospheric pressure and Boyle's law. First, atmospheric pressure is the force of the air above us. And next, we talked about how gases behave. Their volume changes when pressure changes. Now, can you think about a real life example where you have seen this happen? Like a balloon in a vacuum or bubbles rising in water. Next, there's Boyle's law. So, the volume of a gas is inversely proportional to its pressure. So, if pressure goes up, volume goes down and vice versa. And finally, why does this matter? Well, it explains a lot of everyday things. Bubbles in water, syringes, balloons, even how we breathe. Now that we have explored atmospheric pressure and how gases behave with Boyle's law, let's move on to another fascinating concept in fluid, Archimedes' principle.